Hello friends, welcome to Inside Physics. Today we are going to discuss about the polarization of dielectrics. So dielectrics are materials which are a perfect insulators with no free electrons. So how does a dielectric material is useful to us even though it has no electrical conductivity because it is a perfect insulator. So even though it is an insulator, so it actually is useful to store the charges, electrical charges with the help of a capacitor. We already studied that whenever we place a dielectric material in place of a medium between two parallel plate capacitors, the capacitance will be increased because of the dielectric medium between the plates. So what does the dielectric do? The dielectric will be decreasing the electric field between the two plates of a parallel plate capacitor, and thereby also decreases the potential. So thereby increasing the capacitance. So here we understand the polarization and what are the types of polarization in this session. There are four types of polarizations. One is electronic polarization, second one ionic polarization, third one orientation polarization, fourth one space charge polarization. This phase charge polarization is also called interfacial polarization or migrational polarization. So, here interfacial means this is considered to be happening at the interfaces of two particular materials. Interface means it is a border that we will discuss after discussing these three. First of all, we will take up this electronic polarization. What is electronic polarization means? We consider the electrons in a material which is having molecules or atoms or ions. There are electron clouds. The clouds will be displaced towards the positive plate of the applied electric field. If you take a material and apply an external electric field, the electron cloud will be displaced. How it happens? Generally, see, if this is a material and there are some electron clouds which are displaced towards the positive plate. This is the external applied electric field, and inside that there is a material. So all the electrons will be displaced, and the positive nucleus which is stable will not be moved at all, but the electron cloud will be displaced. How much is the displacement? The displacement is not so far, it is not a huge displacement. It is only of the order of only the atomic size, less than the atomic size only. So the displacement is less than the atomic size, and because of this electron displacement, the electronic polarization will be happen. In how much time it happens? When an electric field is applied, it takes around a very short time, 10 to the power of minus 14 to 10 to the power of minus 15 seconds. So this is the time in which the electronic polarization happens. This happens in all types of states of dielectric materials, that means solids, liquids and gases. So how to get the polarization by a mathematical relation? So this polarization can be written as polarization because of electrons is n alpha multiplied by external applied field. So this is the relation. So what is the relation between polarization and the dielectric constant? We know that the dielectric constant is given by 1 plus psi. Psi, where psi is susceptibility. So susceptibility is related to polarization with this relation. Psi is equal to P by epsilon naught E. So by assuming susceptibility and polarization relation, we can replace the susceptibility psi with polarizability, where polarizability is because of electrons Pe and epsilon naught E, where epsilon is the permittivity of free space. Okay, here, so when Pe is written in this way, we can take this as 1 plus, in place of polarization, we can take n alpha E, capital E by epsilon naught E. So here E and E getting cancelled. So what is alpha E here? Alpha E is nothing but polarizability, electronic polarizability. It is different for different materials. So it is different for solids, liquids and gases. So here, if you take a monoatomic gas, so alpha E is considered for a monoatomic gas is equal to 4 pi epsilon naught R cube. For a monoatomic gas, the polarizability or electronic polarizability is given by alpha E is equal to 4 pi epsilon naught R cube. Okay, so if we replace that one here in place of alpha E, so we will get a relation between the dielectric constant and the electronic polarizability. So here, this is how we determine the electronic polarizability, and this happens in almost all the materials, as I already told you. These kind of polarizations may happen as a combined way. That means all the four may be occurring in some materials, or one or two may be dominating in some materials. So all in all, the dielectric polarization contribution, the major contribution will be at least because of one or two polarizations. So next we consider ionic polarization. What is ionic polarization? That happens in ionic crystals. So the term itself says ionic polarizations. You can easily assume that the polarization is because of ions. So ions are found and generally in ionic crystals, in electrolytic solutions, like that. So if you take a ionic crystal just like sodium chloride, this sodium chloride will be having sodium ions and chlorine ions. So when you apply the external electric field to an ionic crystal like sodium chloride, the Na plus and chlorine minus, positive ion and negative ions, are displaced because of the ionic displacement. That is, we can say that is like an elastic displacement. Because of the ionic bond between them, they mutually displaces. The distance will increase up to the up to a mark that ionic that bond will permits the displacement, so that this will not be happening with a big distance. Only up to the distance they will displace, the ionic bond will permits. So this is because of the, I think it can be said as an ionic elastic displacement. Okay, So before applying an electric field, if you consider these two ions have a distance of d between them, the interatomic distance or interionic distance is small d. So the intrinsic dipole moment of this ion, of this sodium and chlorine ion, intrinsic dipole moment before applying the electric field can be taken as Ed. Okay, where E is the electron charge and D is the distance between the two ions. So we all know that dipole moment formula, the distance between the two opposite charges and multiplied by with any one of the charge. So that is what, and here the induced dipole moment after applying an electric field to the crystal, after applying an electric field, the ions will be moved away from each other, sodium ion towards the negative plate, chlorine ion towards the positive plate. So here the induced dipole moment is directly proportional to external applied field, where alpha I is nothing but ionic polarizability. Just like alpha E in the electronic polarization, alpha I, ionic polarizability. So now what is the mathematical relation to get the ionic polarizability for this polarization? So we will directly write the formula. Ionic polarizability is nothing but E square by omega naught square into E. Okay, so where this one, generally we write the polarizability in terms of n alpha I. This is the mathematical relation. N number of atoms, total number of atoms, alpha polarizability constant, applied electric field. Here also, if you observe this one, this is the charge of electron, omega naught is the angular frequency of the molecule or ion. There is a vibrational frequency for each atom or molecule, and that angular, that frequency, that natural frequency of a molecule or ion is considered as here omega. And m, mass of sodium ion, small m, mass of chlorine ion, E, external applied electric field. So this is the relation, and here this ionic polarization happens in around 10 to the power of minus 11 to 10 to the power of minus 12 seconds in very short time. This ionic polarization will happen along with the electronic polarization also. Electronic polarization will also happen in ionic crystals also, but predominantly electronic polarization is more than ionic polarization. This ionic polarization is less compared to electronic polarization. Okay, so next we'll take up what is orientation polarization. Okay, orientation polarization. Orientation polarization is nothing but orientation of polar molecules. Polar molecules are which have a permanent intrinsic dipole moment. So this happens in liquids, gases, and viscous, that amorphous viscous substances. So this orientation polarization is because of the orientation of polar molecules or atoms or ions. So here if you consider a picture of a material where all the molecules, that means dipoles, we will call them as dipoles, are oriented in a random way. Okay, they are oriented in all directions. Okay, where you can say that positive and negative dipole contains polar molecules have a negative and positive center of masses which are not exactly at the same place. The center of mass of the negative charge and the center of mass of the positive charge will not coincide in case of polar molecules. That is why they show some dipole moment, intrinsic dipole moment. So when it is divided into two parts, the negative and positive part, so the all the dipoles have some dipole moment, intrinsic dipole moment, and the dipole moment is oriented in all directions. So these net dipole moment will be zero for this kind of orientation. Net dipole moment is zero because all the dipole moments in all directions will be cancelling each other. So if you apply an external electric field to this material, okay, so the orientation, polarization will be happening. What is orientation? It is dependent on the temperature of the material also. But electronic polarization and ionic polarization is not dependent on temperature, but this definitely depends on the temperature of the material also. These dipoles, which are considered as atoms, molecules, or ions, so these dipoles will be oriented in the direction and aligned exactly in the same way. Considering these kind of orientation, this material now must have a definite net dipole moment. So all the negative charge will be shifted towards the positive plate. This is the orientation pole. Oriented, that means they aligned themselves in the direction of the electric field. Each dipole is aligned itself so that the negative charge is attracted by towards the positive plate and the positive charge is attracted towards the negative plate, and the direction of external electric field is like this. The external electric field can be from positive to negative terminal. So this orientation, polarization, especially happens in liquids and gases. So we can consider the Langevin-Debye theory, Debye-Langevin theory, and the total polarization due to all dipoles given by Langevin-Debye theory can be written as, now we know the general formula, n alpha E. Okay, here alpha O means orientation, polarizability, okay, is given by mu square by 3 kt. Okay, this is the dipole moment, and T, temperature of the material. Okay, Boltzmann constant. Here, this according to this Langevin-Debye theory, the total polarization due to all dipoles is given by PO, means orientation, polarization n mu square by 3 kt into E. Okay, so by this relation we can estimate the polarization. Which polarization? Orientation polarization. So this is how we consider the mathematical relation. And the last one, migrational polarization or space charge polarization. This is also called interfacial polarization also. We see why this is also called interfacial polarization. Last one, migrational polarization. So this happens in some heterogeneous dielectric materials. What are heterogeneous? Heterogeneous materials will have some different electrical properties in different directions, in different directions and different phases also. So in different phases, the electrical properties will be changing. So they are called heterogeneous, but the electrical properties are not uniform throughout the material. So this is considered to be present. The migrational polarization will be present in some heterogeneous dielectric materials and some homogeneous dielectric materials which will have some impurities. It is present in the homogeneous materials also, which are having some impurities. Okay, and with some pores filled with air. Pores filled with air. These are considered to be also impurities. These pores which are filled with some air or some gap inside the material is also considered as an impurity. And another thing we can consider is the inclusion means something is included into the material. Hygroscopic inclusions of hygroscopic water. So this is also considered to be as one of the impurity. So this three, which is impurities, pores and hygroscopic water, any one of them as considered as an impurity, and this especially will be behaving like the impurity in a homogeneous dielectric material. So what does these three will do for a homogeneous material means they change the electrical properties in different phases and in different temperatures and in different directions. So this can be picturized. How this can be picturized? So if you take a dielectric material like this, a dielectric material with positive and negative charge, and here there is a positive and negative charge. So these charges are unevenly distributed inside the material because the material has some impurities. So what happens when you apply an external electric field means they actually form this polarization, the opposite charges, negative and positive charges at the interface of the two materials. So say if this is the material, there is an impurity here. Impurity means there is another material which is filled with some it is a pore with air, or it is it is a material with some hygroscopic water, or it is any other material with like acting like an impurity. So this is the dielectric material and where this is an impurity. This is the interface. This is called the interface of the two mediums. This is medium 1, medium 2, medium material 1, material 2. This is a dielectric material. This is an impurity. So this is the border. At this border, when you apply some electric field here like this, So this at this border, the space charge, that is why it is called space charge polarization. The charges actually migrate to the interface, migrate to the interface. So at the interface, the opposite charges are accumulated at this space. All the space charges are migrated, and at the interface, at this border, at the exactly at the border, they are exactly migrated in the field direction. The negative charges are attracted towards the positive plate, and the positive charges towards the negative plate. It happens at all the places where the impurities are there. So the dipole moment due to a small area with the interface connecting the dielectric medium will be having the dipole moment. All such areas will add up. The net dipole moment is considered to be the contribution towards the migrational polarization. So this migrational polarization is not so big compared to other three polarizations. So we naturally neglect, comparing to other polarizations, we neglect this migrational polarization when we are calculating the total polarization of a material. So if we consider a material which is showing all the four polarizations, what is the total polarization? We just add these four polarizations. The polarization, because of all the four: electronic, ionic, orientation, and migrational polarization or space charge polarization. These are all adding up: electronic, ionic, orientation, and migrational. This we don't consider because this is compared to these three is very negligible contribution. So this one, this we already have a mathematical relation for this, and ionic polarization and orientation polarization, this is considered to be 0. So what we can write ultimately here, okay. So if you write all the relations what we have derived for these electronic polarizations, we will get that n into total polarizability is equal to n into 4 pi epsilon naught r cube. This is for electronic polarizability. Okay, and the second one, mu square by 3k t to, this is for ionic polarization. So next one, the orientation polarization. So orientation polarization here is given by, just a minute, written, this is here I should write E square by n naught square and mu square by 3kt. I interchanged the terms by mistake. So here the total is multiplied by the external applied electric field. So the total polarization due to these three individual polarizations is considered to be with this mathematical relation. This is about the ionic polarization that happens in dielectric materials. What is the use? I already told you. This polarization is required to store the charges. We need some charge if at all required in any electrical circuits. Suddenly, sometimes we require more charge. So dielectrics are very helpful in electrical industry. Okay.